Welcome to the ACSL Ultimate Review. So this is part of the Road to Gold playlist and where I'll be covering all 4 ACSL contests and any material or kind of question that you can find on these contests to help you achieve a perfect score in a gold in ACSL finals. So you should check out my other videos if you want help with any of the other contests, and without further ado, let's get started. So the 3 topics that are going to be on ACSL Contest 3 is Boolean algebra, data structures, and FSAs and regular expressions. So let's begin by going over Boolean algebra. So Boolean algebra is when you manipulate expressions with binary and Boolean values. So these expressions will either simplify to a more concise statement, which will feature variables, typically A through D, or a simple true or a false. So there's a few common Boolean expressions that you need to know, and these are going to be the core of these Boolean algebra expressions. So for instance, while in regular math, in regular algebra, you're going to have a plus, a minus sign, a division sign, etc. In Boolean algebra, you are going to have the and or not, exclusive or, and exclusive nor. So for the and of 2 values, it will only be true if both values are true. The or of 2 values will be true if one or both of the values are true. The not is just a negation statement, so it uses one operator and it turns a false into true or a true into false. An exclusive or will only be true if the 2 values are different from one another, and an exclusive nor will only be true if the 2 values evaluated are the same. So there is an order of precedence when solving Boolean algebra. So you first will begin with a not, then and, then exclusive or, then exclusive nor, and finally the or operator. And operators with the same level of precedence are evaluated left to right. So if there are no parentheses in the statement, then that is the order of operators that you will follow. This is very important because the contest will typically try to trick you with the expressions, and you need to make sure that you are evaluating them in the right order to make sure that you obtain the correct result at the end. These are a few common identities and algebraic laws that you must know. The most important laws for you to know are the identity law and the De Morgan's law. De Morgan's law is the core of ACSL Boolean algebra. It is a law that is most important for you to know and that will 100% appear when you are trying to simplify your expression. I would take a minute to pause the video and review these identities and algebraic laws before continuing, as I'm going to go over a few examples on the next slide. So this is the first example here, this expression B and not 0A, or D and D, or AC. So let's begin. So applying the De Morgan theorem, we know that not 0 and A is the same as not 0 or not A. So we can apply that rule where not 0 is just equal to 1, so we're going to turn that into 1 in our next expression here. Next, we're going to apply the identity law. So when we are distributing this, we get B1 plus B not A plus BDD. We know that D and D is just the same as D, and we know that a value or 1 is the same as 1. So our expression just simplifies overall to B1 plus AC. So applying the identity law again, we know that B and 1 is the same as just B, so our expression overall simplifies to B plus AC. Now notice that this expression simplified to several variables, which means that the outcome of this expression simply depends on what values B, A, and C are assigned to. However, sometimes you will have expressions that simplify to just true or false, or expressions that simplify to only one variable. So it really depends on the formatting of the expression and the variables present. This is the next example. So we have 1 and C, or not D and C, and B plus D and C. So next we can start off by applying De Morgan's theorem. So we know not DC is the same as not D plus not C. Next, we can apply the identity law here. So 1 and C can simplify to just C. Now, applying the complement law here, we see that C or not C is here. In this parentheses expression, it is being used. So we know that that simplifies to just 1. So we can cut C out of that parenthesis expression and replace it with 1. Next, we can apply the identity law that A or 1 is just equal to 1. So not D or 1 is just equal to 1. And it doesn't matter what D is. So that simplifies to 1 and B, or D and C. Next, we know that 1 and a certain value is just equal to that value. So 1 and B can simplify to just B. So our final expression is B or D and C. Next, let's look at the rightmost expression here. And we see we can apply De Morgan's theorem right away. So not A and B is equal to not A or not B. Next, we can apply the identity law because we're essentially saying 0 and this value in the parentheses, right? But 0 and anything is just 0. So we can simplify this and cut off this value, and we're just simply going to get 1 and A or 0. Next, we can apply the identity law. Any value or 0 is just equal to that value, so it's just equal to 1 and A. Next, applying the identity law, any value and 1 is just equal to that value. So A and 1 is just going to equal A. Next, I'm going to go over data structures. So the 3 important data structures that you must know for ACSL are stacks, queues, and binary search trees. So stacks follow a last in, first out structure, meaning the most recently added element is also going to be the element that is removed first if you choose to pop an element. A queue follows a first in, first out structure, meaning that the first element placed in is going to be that element that is going to be popped out of the structure the next time the user calls the pop command. The binary search tree is used for finding, parsing, inserting, and deleting data. It's essentially a data structure that's used to store data. And it can be used for iterating through and finding data very quickly. It's very popularly used because it has a big O of log n, so it essentially means it doesn't take that long to find an element in the tree because it is sorted. So these are some images I added that I think are useful to visualize. So as you see the queue, that first element that you place on top of the pile, that's going to be the first element you're going to take out. It's like a stack of books. You're going to take whichever one you place. The first one that's going to be accessible for you to take is the most recently placed one at the top of the queue. For a stack, though, I picture it on its side so you can see how you're taking out elements from the right side and you're putting in elements on the left side, and the elements on the left side will gradually transition. But before you can take out that most recently placed element, all the elements before that have to be taken out first. So for stacks and queues, there's a few methods that you have to know. So push is one that will add the element to the stack or the queue. There will always be a parameter in this method, and that will be the item that you're adding to the list. So in both a stack and a queue, pushing an element results in it being placed at the top of the stack or the queue. For a pop, in a queue, items will be removed from the bottom of the list, while in a stack, the most recently pushed item will be removed. So applying pop to an empty stack or queue results in it having the value of nil. So sometimes it will result in nil being your final value for a stack or a queue, and that could be an answer on your ACSL multiple choice. So make sure you know what that means and how you can get it. Now, here is an example of me applying the same operations to an empty stack and an empty queue, and you'll see quickly how the values at the end turn out to be different. So here we're pushing A and B, so I'll go over the stack first. We're adding A and B to our list. Now, in a stack, when we do pop, we're going to pop the most recently added element, which is B, so we're popping that. Now we're adding C and D, C, D, but then we're popping the 2 most recent elements. We'll pop D, then we'll pop C. So that's why they have these little X's next to them. Now we're adding E to the list. So now our final list is just A and E. Now, versus a queue, we're adding A and B, but then we're popping. We're going to pop the first element we added, which is A. Next, we're going to add C and D, but then we're going to pop 2. So we're going to add the 2 oldest elements in the list, B and C. Those were at the bottom. Next, we're going to push E to the list. So E gets added to the end. So then our elements left are just D and E. So notice how you got different results based on whether you are using a stack or a queue as your data structure. This is very important in ACSL again because they will try to trick you and you have to read closely into the lines and determine whether you're working with a stack or a queue in a particular problem, or you will get different results. Next, binary search trees. So for each tree, there's a few words that you must know during the contest, which you may be asked to solve for or to list in your multiple choice. So the root of the tree is always the top node in the tree. It will have a depth of 0. The children are the two nodes you will find beneath a parent node. And leaves are going to be nodes that don't have any children. Siblings are going to be the two nodes with the same parent as each other. Depth is the height of the tree, so how many generations are present, if you will. So the external node is another way of saying leaf node. The internal path length is the sum of the depths of all nodes, and this is counting external nodes. So that little segment is wrong. We are counting the depth of all nodes. The external path length is only the sum of the depths of the external nodes. So the external path length only considers the depths of the leaves, if you will, of the binary search tree. So there's 3 different kinds of traversals that you may be asked for on ACSL: the in-order, pre-order, and post-order traversal. So the in-order traversal will visit the left child, then its root, and then the right child in its traversal, while pre-order will do the root, left child, then root, left child, right child, and so on, while post-order will do the left child, right child, and then the root. As an example, to apply these vocabulary words, this is a word MENARD, and I constructed a tree to represent this word. So if you're ever asked to construct a tree based on a specific word in ACSL, there's a very simple method how to do it. They essentially want a sorted tree. So we're going to do M, that's the first letter, then E comes before N, which is why it's to the left. A comes both before M and E, so we put A to the left again. N goes after M, so it goes to the right. R is after N, goes to the right. D would actually be before M, so it would be here, but after E. So D would be placed right here. But I'm going to leave D where it is, in our case, just so I can get accurate depth, internal, and external path length values. So in this tree, M is the root of the tree, it's at the top, and its children are E and N. The leaves of the tree are the nodes with no children, so that's A and D. E and N are examples of siblings. This tree actually only has one pair of siblings, which are E and N. The depth of the tree is 3, because the depth of M here is 0, depth of E and N is 1, depth of the A and R is 2, depth of D is 3. Internal path length is 9. We get that by adding 1, 1, 2, 2, and 3 together to get 9. External path length is 5 because we're adding in a depth of 2 and a depth of 3. FSAs and regex are the last category on ACSL Contest 3. So these are the few patterns that you will see in a regex expression. So I would recommend that you pause the video and read over these patterns before we proceed. It is important that you memorize these patterns for your multiple choice because that was what the questions are going to be based on. So first, let's begin with an FSA. An FSA is formatted as like the image below, and this one in particular represents X, X star, Y, Y star. So the reason it does so is because we have an X, but now we have an optional X. We could loop an infinite amount of times around B, or we could loop none, which is why we have a little star up here. As you noticed up here, the asterisk instigates 0 or more occurrences. So that's why we have a little asterisk after B and after C. So XY and then XXXXX, Y, 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 Y are the two possible expressions that this could result in. Granted, this could result in an infinite amount of expressions because we could have an infinite amount of X's or Y's, but notice how we always must have a Y after the X. We can never have a combination of X, X, Y, and then X, right? We have to have an X, a said number of x's at least 1 and a said number of y's at least 1. So this expression xyx is impossible for this expression. So these are the kinds of questions that you will be asked for is what expression is possible? What expression is impossible for the following FSA or for the following regular expression? So here are two examples using the knowledge that we just learned. So which of the following strings are valid? So here we have 1, so we must start with a 1, right? Because we have a 1, we don't have like an asterisk or anything after this 1, right? Our expression has to start with 1. So we can already cross off A. Now we have a said number of 1s, we can choose how many. So we could have at least 1 because of this one, or we can have an infinite number of 1s. That's noted. Now in here we have this expression or this expression, and that must be part of it. So we must end with either a 1 or 0 or a 0 or 1, and we must start with at least 1. Now let's see which expressions match that constraint. So we start with a 1 right here, I see that, but we're not ending with a 1 or 0 or a 0 or 1, right? This is 10, yes, that's what we are ending with, but we need to also at least 1 at the start, at least 1, or else our expression isn't going to be valid, so that doesn't work. Next, we have D. D has a large number of 1s, that's fair, but it also ends in 0, 1. So D actually does follow the rules of this expression. B, however, doesn't end with a 0, 1 or a 1, 0, so we know that B isn't valid. So that's how you would go about solving these kinds of expressions. The next expression that I'll go over is this one, example 2. So we start off with an A or a B, so that's how we know our expression must start with A or it must start with B. Now both of them, but all three of our choices start with A or B, so we know that in that case, that's fine. Next we have C and a question mark. So question mark there means that there's either one or none occurrences of C. Again, we don't really see an infinitely large number of C's here, which means that all of our expressions follow this rule. A D and a plus sign. So a plus sign means that there's one or more occurrences of D, right? So we need at least one occurrence of D. Again, all our expressions follow this. And now we have a dot. So a dot is a wild card, right? We have a little asterisk after the dot, which means that there will be a random element and there will be one or more or 0 occurrences of said element. Next, we see a range, A through Z, which means we're just going to have one element in that range, A through Z, so just a random letter. This is equivalent to just putting a dot. Well, dots also factor in numbers, so in a way it isn't, but all of our expressions have only letters, so it doesn't matter to us in that way. Not A through Y, so it's basically saying that it can generate a Z or it can generate a number. So because we don't have any numbers in our regex, we know that there must be at least one occurrence of Z in our expression. Now, this is important because both B and C do not have that occurrence of Z, which means that they don't follow the rules of our regex. So A is the only one because we start with an A, we choose to have one occurrence of C, we have one occurrence of D. Our wild card here is E. One element A through Z, that happened to be E, and an element that's not in the range of A through Y, and that's C. So that's how we know that A does follow the laws of that expression. Now, this is all I have for you all today. I hope that this review was helpful. I highly recommend that you look at the ACSL wiki. These videos provide a good summary of the wiki, but the wiki also goes a lot more in depth over some of these topics. So if you have extra time before your contest, I recommend that you look at those before to prepare. I'm going to be releasing a contest for video very soon, and I look forward to seeing you guys again in the next video. So thank you for watching, and bye. Good luck.